seal distributor personnel. We're going to talk a little bit about the principles of sealing and elements of seal design that affect a seal's performance. But before getting into that, we want to talk a little bit about terminology. Basically, products we're going to be talking about primarily are elastomeric seals, elastomers. An elastomer is a product that is elastic in nature. It can be compressed, it can be twisted, it can be stretched, and when it's released, it will return to its original shape. Elastomeric seals are basically the seals of design for rod-type sealing applications. We'll also talk about inside diameter, outside diameter, cross-section, height, static and dynamic seals, symmetrical, asymmetrical seals, and then extrusion gap. Here we see on an illustration of the inside diameter and outside diameter of the seal. I think all of you are familiar with those terms. The inside diameter of the seal is going to relate to the groove diameter on the piston. Outside diameter of the seal is going to relate to the groove diameter on the head. The outside diameter also will relate to the piston diameter or the bore of the cylinder. The height of the seal is the distance the seal extends above a flat surface. That's going to relate to the groove width. And finally, the cross-section is the difference between the outside diameter of the seal and the inside diameter of the seal divided by 2. So if we have a 2.5-inch outside diameter, a 2-inch inside diameter, the difference is a 1/2 inch divided by 2 gives us a 1/4 inch cross-section. That's important because it's going to relate to the groove depth in our cylinder, but also because most suppliers' catalogs talk about used seals and other seals are organized by cross-section. So they start generally with the narrowest cross-section, 1/8 of an inch. They work up through the various cross-sections, and within each cross-section, seals are organized by the inside diameter. So it makes it easier to find a particular seal that you might need to use. Here's an illustration, a cutaway of a hydraulic cylinder, illustrating the static and dynamic seals. This particular cylinder has 3 seals in a static location. Static seals are seals that have no relative motion. So we have 2 end caps on this cylinder. We have an O-ring at each end cap. These seals see no relative motion. They're trapped in this gland area. The O-ring underneath the piston on the cylinder rod, likewise, sees no relative motion. It's trapped in this gland and basically is relatively motionless. Now, even static seals will have some movement involved within the confines of this groove. As pressure is transmitted through the fluid throughout the hydraulic cylinder, pressure will flow in this area here, push against this O-ring, and will deform the O-ring against the back of the gland. So this O-ring under pressure, because it's elastomeric, will be compressed, and then it will be released as the pressure releases. So there will be some slight movement here. Same is true underneath the piston. There will be some slight movement of the O-ring within this space, but it will be very, very minimal, as no relative motion involved. Our dynamic seals are the 2 U seals on the piston and the U seal on the rod. The ID of the seal on the rod is dynamic because there's relative motion across this surface. The OD of the seal, however, is static because this seal is relatively motionless in the groove. The piston seals, the OD of the seals are dynamic. The ID of the seals are static because they are relatively motionless in these grooves. So that's the difference between dynamic and static seals. Now there's 3 types of dynamic sealing. There's reciprocating sealing, where we have a shaft that moves back and forth in a linear fashion. Okay? This is the type of sealing that we're going to be talking about today. We're going to be talking about elastomeric dynamic seals in reciprocating applications, hydraulic cylinders. You also have rotary motion, which would be a shaft on a hydraulic motor or pump, and you have oscillating motion, where you have a shaft that moves in and out and rotates at the same time. But we're primarily going to be talking about reciprocating elastomeric seals. There's also symmetrical and asymmetrical seals. This would be our symmetrical seal, having similarity in size, shape, and relative position of corresponding parts. The asymmetrical seal has no balance or symmetry. Here we can see if we draw a line through the middle of the cross-section of the seal, each half of the seal is a mirror image of the other. With the asymmetrical seal, this half of the cross-section is shaped differently than this half of the cross-section. So a symmetrical seal can be used interchangeably as a rod seal or as a piston seal. An asymmetrical seal, however, can be used only as a rod seal or only as a piston seal. It cannot be used interchangeably. Asymmetrical seals were developed in the 1960s, and they were developed as a way to improve seal performance. But prior to that time, all U seals were symmetrical in nature. Dijsselgren found that one seal lip configuration worked better for sealing in a dynamic application. Another seal lip configuration worked better for sealing in a static application. By combining the two different types of lips in one seal, you had a better performing rod seal or a better performing piston seal. So they were able to improve seal performance in low pressure dynamic sealing applications. The advantage to the symmetrical is that it can be used either as a rod seal or a piston seal. The advantage to the asymmetrical is that it works better in a dynamic low pressure sealing application. And then extrusion gap. Extrusion gap is the space between any two machined parts in a hydraulic cylinder. When you have motion involved, when it's a dynamic application, you have to have a wider gap between the metal parts than if it's a static application. When you have a wider gap, when you have pressure against the elastomeric seal, the seal will try to extrude into that gap. The wider the gap, the easier the extrusion. So by controlling the extrusion gap, we can improve the performance of the seal. Usually it's economics that determines this gap. Okay? The wider the gap can be, the less costly it is to machine the parts that go together. So you try to provide a seal that will work in a particular application where you are controlling the extrusion gap. Now, let's look at how elastomeric seals perform. Elastomeric seals perform by conforming to the metal surfaces on which they come in contact. The better the conformity to the sealing surface, the better the seal and the less leakage that we're going to have. And elastomers will conform better to smooth, rounded surfaces. So the smoother we can make the surface, the more rounded the irregularities on the surface, the easier it is for the elastomeric seal to conform to the surface. Now, let's look and see how we can improve the conformity of the seal. See what effect pressure has on seal performance. Pressure comes from two sources. We have mechanical squeeze and we have system pressure. Mechanical squeeze is designed into the seal by the fact that the seal is designed with a larger cross-section at the sealing lips than there is space in the groove or in the gland. So by having a larger radial cross-section, the seal is squeezed mechanically, and the sealing surface conforms to the sealing lips conform to the sealing surface. system pressure helps improve the sealability, because as the force is transmitted through our incompressible hydraulic fluid against the seal, forces the sealing lips even more tightly against the sealing surface. So therefore, we can say that pressure aids sealing. More pressure in the system, the tighter the conformity of the sealing lips to the sealing surface, and the better the sealability. At low pressure, our seals will have a shape. At high pressure, the seals deform due to the pressure and become a glob, very technical engineering term there. Seals will become a glob in the groove. The more pressure that's applied, the tighter the conformity of the sealing surface. At low pressure, the seal has a shape. The only conformity is due to the radial interference that's designed into the seal. So the more pressure, the better sealability. Here we see an illustration of Pascal's law. Pressure in a confined body of fluid acts equally in all directions and always at right angles to the containing surfaces. So we have our fluid in a chamber. We apply pressure. The more pressure we apply, the more force is transmitted through the incompressible fluid, and it pushes outwardly at right angles to all these surfaces. If our seal were contained in this fluid, that fluid would operate on the seal, pushing it into tighter conformity with the sealing surface. So therefore, we can say that pressure aids sealing. Most all of our seal leakage problems occur at low pressure. It's at low pressure when the seal shape affects seal performance. Okay, now, here we see an illustration of an O-ring in its free state. Here's the O-ring after it's been installed in the groove, in the gland. Okay, you can see how the O-ring is being compressed radially and how it changes shape axially. By compressing the O-ring radially, we're improving the conformity to the sealing surface into which the O-ring is coming in contact. If we have a static sealing application, we have flow from one direction. The flow pushes the O-ring to one side of the groove. When we have a resistance to flow, we have an increase in pressure. The greater the pressure, the greater conformity to the sealing surface, and it reduces our leakage path. This is the scenario we have with a static seal. However, dynamic sealing, we have relative motion involved. We may have flow coming from alternating directions. First, you have flow from the left side. You have flow from the right side. You actually have the seal moving back and forth in the gland or in the groove. Then you have a surface moving across the seal. This is our relative motion that's involved in the seal. So it's much more difficult to seal effectively in a dynamic sealing application like this than it is in a static application. Because as this seal moves, it wants to twist and turn. And it's maintaining the stability of the seal in this groove that gives us improved sealability, especially at low pressure. Now, let's see what kind of dynamic sealing problems we might have. First, we encounter friction. Friction is a bigger problem in dynamic sealing than static sealing because you have the relative motion of the seal along the sealing surface. And typically, if you don't have enough lubrication, you create friction. Friction creates heat, and it creates wear. Extrusion is a problem in dynamic sealing. It's also a problem in static sealing, but it can be a bigger problem in dynamic sealing because as you have the movement of the rod extending, you're going to want to pull the seal along with it into the extrusion gap. I mentioned wear being a function of friction. You have friction, you have wear. Due to the relative motion, you're going to have wear on the seal. Stability is a bigger problem. Notice before we talked about stability. The more stable we can keep the seal in the seal groove, the better the sealability is going to be at low pressure. And then finally, sealability. If we can overcome these first 4 dynamic sealing functions, we will achieve a high level of sealability in our seals. Now, seal engineers and you as repair people can use these dynamic sealing problems to evaluate different types of seals for different applications. And we will do this as we move along. There's 4 elements of seal design that affects a seal's performance. There's the shape of the seal, there's the lip configuration of the seal, there's improvers, and there's the material from which the seal is manufactured. In discussing seal shape, you must remember that there's 3 basic shapes that seals can take: round, square, and rectangular. As we move from round to square to a rectangular, the stability of the seal in the seal groove improves. It's more stable. We're also concerned about the amount of gland fill, or the space in the groove that the seal shape occupies. And we're concerned about that because of stability. Okay? The more stable the seal, the better sealability that we're going to have. If you have a round shape and a very large groove, you have a lot of space for the seal to move back and forth in the groove, so you have less stability. So when you're designing a cylinder, you can pick the seal that you want for a particular application. You design the groove for that seal. However, when you're in a repair application, you must pick a seal which will fit the groove that you have. You always want to pick a seal that has the appropriate amount of gland fill to maximize the stability of the seal. Now, there's 2 basic types of seals. And when we analyze these 2 basic types of seals, we're talking about lip seals or squeeze seals. Here we see a pure lip seal in its free state and a pure squeeze seal in its free state. When we install the seals, you'll notice how the lips on the lip seal get more vertical in nature. So what we're doing is we're taking these lips, we're forcing them inwardly so that there's a more vertical relationship to the surface. With our pure squeeze seal, however, when we install it, we're actually compressing these sealing lips, and as we compress these sealing lips, we're actually displacing seal material. So that as we move the lips inwardly, install the seal, you'll notice that material is displaced and we've changed the shape of the seal. By doing this, it creates a much higher radial force outwardly against the sealing surface. So, with our lip seals or squeeze seals, we're concerned about friction, concerned about wear because of increased friction, and then ultimately we're concerned about low pressure sealability. Because we've already mentioned that most of our sealing problems occur at low pressure. At high pressure, shape has very little to do with sealability. Shape is only important at low pressure. Here we see our illustrations again, and we see with our pure lip seal, this being a very thin wall lip, takes very little force to press these lips inwardly, and therefore it creates very little radial force outwardly to give us a very low degree of sealability. Now the advantage is we have low friction and low wear. The disadvantage, the low radial forces, we have relatively low sealability at low pressure. With our pure squeeze seal, however, when we displace the seal material, changing the seal shape, it increases a lot of radial force at the seal lip sealing surface interface. So we achieve a very high degree of sealability at low pressure, but to achieve this sealability at low pressure, we have a high degree of friction and a high degree of wear. So it depends on where you're using the seals as to which type of seal you would select. If you have a application that is very sensitive to friction, you would want to use a pure lip seal. If you have a application that is very sensitive to sealability and is going to operate at high pressures, then you can give up the friction to achieve the higher degree of sealability. Now, this would be true at low pressure. Okay? At low pressure, our pure squeeze seal is going to give us a high degree of sealability. What would be true at high pressure? Which seal is going to seal more effectively, the lip seal or the squeeze seal? Well, it's a trick question because at high pressure, if you remember, we said the shape of the seal has very little to do with sealability. At high pressure, both of these seals are going to seal adequately as long as they don't extrude. Okay? So assuming there's no extrusion, both seals will seal effectively at high pressure. It's only at low pressure when we have most of our sealing problems where you need to worry about a choice between a pure squeeze seal and a pure lip seal. Now, rarely is there a simple decision between two seals. In the real world, there's many different seals to choose from. And here we see a continuum of 9 different types of seals, ranging from our pure lip seal at this end of the continuum where we have low friction, low wear, and low sealability, to our pure squeeze seal at this end of the continuum where we have very high friction, very high wear, but a very high degree of sealability at low pressure. And then the compromise seals in the middle, they have varying amounts of friction, wear, and sealability depending upon the application. So if we have, as I mentioned, a pneumatic application where friction and wear is a problem, we would want to select a... Here we see a 9-point continuum starting with our pure lip seals on the left and ending with our pure squeeze seals over here on the right. You can see with our pure lip seals we have low friction, low wear, but we have a low degree of low pressure sealability. With our pure squeeze seals we have high friction and wear, but we can accomplish a high degree of low pressure sealability. These seals in the middle, these are compromise seals. They have varying amounts of lip thickness, which increases the radial forces the further up the spectrum we go. And they have varying amounts of friction, wear, and sealability depending upon how thick the lips are and how much radial force is exerted by the sealing lips. Now, we can use this continuum and the other elements that we've discussed to apply them to actual seal profiles and evaluate how they might perform in different applications. Here we see a round shape, which we would typically refer to as an O-ring. And our O-ring shape is a solid mass of material, and as such, it would rate a number 9 on our continuum. It would be a pure squeeze seal because it's a solid mass of material. Being a squeeze seal, the friction would be high, and the wear would be high. So being a squeeze seal with high friction and wear, we would assume sealability would be high. But what's the problem with our O-ring seal? Well, remember when we talked about shapes, we said that square is better than round and rectangular is best. So the round shape is the least stable of our seal shapes. So our stability on our O-ring seal is very low. So while we otherwise might think the sealability would be high, the round shape detracts from or reduces the performance capabilities of the O-ring to where it is no more than a medium performing seal. Now the next profile we have would be that of a quad ring. Here we have a 4-lobed seal. Now instead of a round profile, we have a square profile. Okay, this is still fairly high up on the continuum, probably rated about an 8 because we do have a little free space around the outside edges here. But it's very high up on our squeeze list, friction is high, wear is high. What about stability? We have now improved the stability of this seal over the O-ring because now we have a square configuration instead of a round. So our sealability is going to have improved. So we have a better performing seal from the quad ring than we do from the O-ring. Here we have a seal profile that would be typical of a pneumatic cylinder. Relatively thin wall lips. We have a square profile where the height of the seal is the same as the cross-section of the seal. Because of the thin wall lips, we probably would rate this seal maybe about a 3 on our continuum. Because of that, our friction is going to be somewhere in the low to medium range. Our wear is going to be low to medium. The square profile is medium profile from a stability standpoint, so stability is going to be medium. Our sealability, we're down in this area here, low to medium. Okay, but that typically is adequate for a pneumatic cylinder application. This seal, however, over here is a square profile seal. Height and the cross-section are the same. The type of seal is probably about an 8, very high up on our continuum, giving us high friction, high wear. Stability, though, is basically only medium. So our sealability isn't going to be as high as it might be because of the relative instability of the seal profile. So giving us a sealability somewhere in the medium or high medium range. This seal would be very good to replace an O-ring, a dynamic O-ring seal, with a seal like this, where you had an application where the O-ring was not stable enough, was not performing satisfactorily. You could use a square B seal like this. Now, the bottom row of seals are all rectangular in shape. That is, the height of the seal is greater than the cross-section. Our stability is going to be extremely high. This seal is a symmetrical seal. You look at the thickness of the seal lips. We're probably going to be around a 6 or so with this particular seal. The friction is going to be medium-high, wear is medium-high. Stability is very high, which is going to improve the overall performance of this seal. This seal is our asymmetrical seal. It can be used only as a rod seal or only as a piston seal, not interchangeable as with the symmetrical. You'll notice that one lip is longer, giving us increased stability over the rectangular shape. This would be the static side of the seal. The dynamic side of the seal, the lip is a little bit thicker and a little bit shorter. Another feature of an asymmetrical seal is that it usually is designed so that the static side of the seal fits much more tightly against the static surface, cutting off a low-pressure leakage path on this side. So we're looking at probably a seal in the 7 range here. Friction is medium to high, wear is medium to high. Stability is extremely high. The sealability of this seal is going to be higher than this symmetrical seal. It's going to be very high. This particular seal, also a rectangular seal, so stability is very high. It gets its performance advantage from the standpoint that we now have an energizer in the seal, which significantly increases the radial loading of the sealing lip against the sealing surface. So it's a pure squeeze seal, probably an 8. Friction is high, wear is high, stability is very high, sealability is very high. But you could not use this particular seal in a low-pressure application where you have to overcome a lot of frictional drag. So it gives you a little bit of idea of how to analyze different seal performance. And remember, this is only true for low-pressure applications, low-pressure situations. If it's high pressure, all of these shapes seal effectively. It's only at low pressure, but the seal shape affects seal performance in a sealing application. Now, the lip style that's incorporated into the seal shape might be referred to as a fine-tuning element of the seal. There's 5 basic lip designs that can be used in our seals. There's the B lip, the D lip, a round lip, a square lip, and a scraper type lip. Here we see an illustration of a line drawing of a seal, and this portion is the sealing lip of the seal. Here we see a line drawing of the shape of the seal lip. This would be a B lip. Here's a line drawing of the D lip, the round lip, square lip, and scraper type lip. Scraper type lip would be typical of a piston cup. When the seal is installed in the cylinder, you can see how the lip deforms. By squeezing the lip against the sealing surface in this area, it creates a pressure pattern. And the distance that these horizontal lines extend to the right indicate a relatively greater amount of force exerted by the seal lip at that particular point. You can see that the B lip has a greater amount of radial force exerted against the sealing surface than the D lip. And the D lip a greater amount than the round lip a greater amount than the square lip a greater amount than the scraper type lip. So the further these pressure patterns exert to the right, better conformity to the sealing surface under low or no pressure. Here's another way to look at that same thing. Sealability comes from conformity at the best point. Here we see the B lip sees the highest degree of sealability because of the greater radial force exerted against the sealing surface. Part of that has to do with the hydroplaning resistance, which comes from the film breaking ability of the seal. Okay? Because the B lip actually conforms better to the sealing surface, it does a better job of breaking the fluid film that adheres to the seal or the sealing surface when the rod extends. So we have a better degree or higher degree of sealability from the B lip than we do from the D lip. You'll have a wetter surface with the D lip than you do a B lip. With the round lip, we again have more fluid getting underneath the seal lip. Same is true of the square lip and the scraper lip. Square lip and a scraper lip, it's rare that you would ever see these used in a rod sealing application. Used in a piston application, like a piston cup or a Teflon type piston seal, you have a little fluid bypass at very low pressure. Typically have no problem with it in a piston sealing application because the fluid is contained inside the cylinder. But you would not want to use these for a rod sealing application. Another thing to consider when selecting seal lip designs is the amount of contamination that is in the system. B lips and round lips typically are not very good to use with contamination because the contamination tends to wedge itself into this interface area between the sealing surface and the seal lip. Same thing happens with the round lip. So it's more wearing on the sealing surface and more abrasive and wearing to the seal lip itself. The straight lip, the D lip, is good. The square lip is good because it keeps these contaminants out in front of the seal interface. And the scraper type lip is even better because it allows the contaminants to flow up and away from seal lip sealing surface interface. Now, you might say, well, why don't we just use the B lip for almost all applications because it seals so much better? Well, there are some applications where actually you want a heavier film of fluid on the surface to be sealed. One of those would be in a pneumatic cylinder application because there's a lot of money spent to atomize fluid into the pneumatic system to lubricate the internal components of cylinders and to help reduce rust and so forth from moisture that gets into pneumatic systems. So in a pneumatic system, most all of your seals will have D-type lips to allow for a more fluid on the surface of the components. Another application where you do not want to use a B-lip is where you have two loaded U-seals on a piston in a double-acting application. In that application, the loaded B-lips can actually seal too effectively and cause pressure trap between the two seals. On a double-acting piston application, on the side of the piston where there is no pressure or low pressure, the seal must allow enough trapped pressure to bypass the seal lip so that it doesn't build up between the two seals. However, if the low-pressure seal lip is sealing too effectively, you trap pressure between the two seals, and if you trap enough pressure, you can actually cause the seal to extrude on the piston, trapping seal material between the OD of the piston and the bore of the cylinder. By trapping this material, it creates a lot of frictional drag, a lot of heat. The heat softens the seal material, allowing it to extrude even more, and creates a catastrophic failure. In some cases, that pressure trap can be so great that it can actually fracture part of the piston. So when using loaded U-seals on a piston, seal manufacturers design the D-lip so that you have a little bit of leakage on the low-pressure side so you don't trap pressure. If you are using two B-lips on a double-acting piston with the loaded U-seals, you need to remove one of the energizers from one of the seals. That will help reduce the low-pressure sealing capability of that seal so it minimizes the opportunity for trapping pressure. It has no effect on the high-pressure sealability of that seal. It only reduces the low-pressure sealability. Now, another element of seal design is improvers. What are improvers? Well, improvers will help us solve one or more of our 5 dynamic sealing problems. There's something that's added to the seal to improve its performance. Typical improvers would be backup rings, anti-extrusion rings, expanders like the O-ring or quad ring in a U-seal, or the expander ring underneath a Teflon piston seal. Reinforcers. A typical reinforcer, if you think about V-packing, you have homogeneous rubber rings, and then you have neofab rings. The neofab rings are a neoprene cotton fabric material that are coated with rubber that enables the V-ring to be used at higher pressures. And then multiple rings would be examples of improvers. These would be redundant sealing. Okay, one type of multiple ring could be a V-packing. Okay, and there's various types of V-packings, multiple lip seals. Here we see non-gland sensitive multiple lip seals. And these are non-gland sensitive because by squeezing these seals axially, they have no effect on the flare of the radial flare of the lips. The radial flare of the lip is designed into the seal, and they cannot be adjusted by squeezing on them because of the center leg down through the center of it. Here's a different type of non-gland sensitive ring, and again, no adjustment on the lips of the seals. The V-packing, however, on the other hand, is a gland sensitive type of ring. It has multiple rings which seal more effectively, but when you shorten the axial length of the gland, you're actually squeezing the sets together. This adapter ring pushes up into the cavity of this free ring, causing this lip to flare out with a greater radial flare. The crown of this V forces into the cavity of this one, causing it to flare out, and so on up the stack. So by shortening the axial length of the gland, you can create a greater amount of radial flare of these lips and make the set adjustable. Another improver is the backup ring. The backup ring is designed to reduce the extrusion gap. This would be the extrusion gap. You can see how the backup ring cuts this gap down significantly. You have two metal moving parts. You have to have some space between them. This is a non-metallic ring. You can have a much tighter clearance here than you can with metallic parts. This backup ring is a flat-sided backup ring. This backup ring is a contoured backup ring made popular by Parker called a par back. The concept here is that as the O-ring is deformed against the sealing surface, it pushes the O-ring back away from the extrusion gap. This is mostly a matter of personal preference between the flat backup ring and the contoured backup ring. They both work satisfactorily. Depends on which one you have a preference for. Here we see another improver. This is a T-seal. T-seal is an evolution of the O-ring. A T-seal occupies the same amount of space as occupied by an O-ring, but it has two backup rings built into that space, which gives much better extrusion protection against the nitrile sealing element. It has the same sealing lip as an O-ring does, but it has a flat base, which gives a lot greater stability to the seal in the seal groove. T-seals were originally developed for the aircraft industry, where they were used in landing gears and control surfaces on aircraft, the actuators that control the control surfaces on aircraft. They operated at a lot higher pressures than O-rings because of the built-in backup ring and the extra stability designed into the seal by the flat back. Here we see what's called a wide-base T-seal. Wide-base T-seal was developed to replace an O-ring and two backup rings, which are used in double-acting applications. This seal also retains the round sealing lip like the O-ring, but it has a flat base, which gives much greater stability to the seal, and it has the backup rings built into it as an O-ring and two backup rings. The advantage here is the flat base, which gives a lot more stability to the seal in the seal groove. And our third example is a further evolution of the T-seal. Here we have what's called a four-piece piston seal or a capped piston seal. And here we have a T-shaped sealing element with two backup rings, which is the same design as taken from the wide base, but then the seal designer has put a Teflon sealing element on top of the T-shaped expander ring. Now you'll notice that this sealing element is square. It's actually rectangular, but would be referred to as a square lip, which gives better sealing performance in a contaminated environment. Teflon also has much lower frictional drag, and so you would have a less frictional drag on a piston using this particular type of seal than you would a piston using this particular type of seal. So a further evolution or improvement in the seal design. And here we see our three types of U-seals again. Our symmetrical U-seal, which was basically the standard of the industry prior to the 60s. The introduction of the asymmetrical seal to reduce low pressure leakage on the static side of the seal, improve stability of the seal in the groove, and to give a better, more consistent contact surface between the dynamic sealing lip and the sealing surface. This was introduced in the 60s. Then we have the loaded U-seal, where the expander or energizer creates a greater radial force of the sealing lip against the sealing surface, giving us improved low-pressure sealability. Now, another element of design is the type of material from which the seal is manufactured. These are very common types of materials that you encounter in most hydraulic seals. Here we see a brief description of each of these types of seal compounds. This same information can be found in our seal catalog on page 344. The nitrile or Buna-N provides excellent resistance to petroleum-based fluids and to air, and it can be compounded for a temperature range of a -40 up to 240 degrees Fahrenheit. Its hardness can range from 40 to 90 short A. We will talk about the measurement of hardness in just a few minutes. Neoprene is typically used for refrigerants, for high alkaline oils, and some other compounds, not for use in phosphate esters, nor is nitrile for use in phosphate esters. Temperature range on neoprene is a little bit higher than the nitrile, and its hardness range is about the same, from 40 to 90 on the shore A. Polyurethane exhibits outstanding mechanical and physical properties compared to other elastomers. Temperature range can be from a minus 65 to 100, and there's actually some compounds that will range as high as 275 degrees. Hardness can be from 40 to 95 on the shore A scale, and its inherent toughness and abrasion resistance is desirable in hydraulic systems for high pressures and shock loads. You can allow for larger metal tolerances with a urethane seal than you can with a nitrile seal at higher pressures. Fluorocarbon is another term for Viton. Viton is a trade name of DuPont. Fluorocarbon is a more generic name. It was introduced in the 50s. Temperature range from minus 20 to 400 degrees. One of the primary principal reasons that you use it is for higher temperature elevations. Also, it is compatible with selected phosphate ester fluids. It cannot be used with Skydrol, some other types of fluids, but it would be used primarily for higher temperatures in petroleum-based fluids and also for some phosphate esters. Ethylene propylene has a temperature range of minus 20 to 300, hardness from 40 to 90 shore A, excellent resistance to Skydrol and other phosphate ester fluids. So that would be the principal reason you'd use EPR, is because of its compatibility with a wide range of phosphate ester fluids. And then Teflon. Teflon is not an elastomeric type of seal, but because it's used extensively for sealing applications, I included it here. It's a tough, chemically inert polymer. Working temperatures from minus 300 up to 500 degrees, and hardness usually around the 98 shore A. Teflon seals are tough, they're impact resistant, and they exhibit very, very low friction. They can be used on very, very smooth surfaces. Has very poor memory, however. When you go to install a Teflon seal, they're very difficult to install because they'll stretch and they do not want to come back to shape. So if you heat the seal slightly, as outlined in our seal catalog, it'll make it easier to install, and then put some type of constriction around it, like a wear ring, and clamp the wear ring down very carefully so as not to damage the surface. And as the Teflon material cools, it will shrink back to size and make it easier to install. One of the problems with Teflon is what's called cold flow or creep. We think in terms of an elastomeric seal like nitrile or urethane, we would call this extrusion. But when talking about Teflon, they call it cold flow or creep. And that is the characteristic of the seal material to flow under pressure between the two metal gaps of the cylinder. They try to control that with the addition of certain types of fillers. Common fillers in Teflon seals are glass, fiberglass elements, bronze elements, carbon, graphite, and mineral. And different fillers will have different characteristics and might be used in different applications. Here's an illustration of the hardness, measuring the hardness of a seal. This is an instrument that measures seal hardness. And the hardness, the relative hardness of the seal is referred to as the durometer reading. Generally, there's a plus or minus 5 on this scale. When seal manufacturers are making seals, they do not measure the hardness of the individual seals because the shape of the seal will affect the material's hardness. But rather what they do is manufacture a test plug, they cure it, and then they measure the hardness of that test plug to verify its hardness reading. And like I said, there could be a plus or minus 5 on this scale. For most purposes, for our purposes, for your purposes, you can measure an O-ring or you can measure a U-seal and get pretty darn close to what the proper hardness is supposed to be. Now, the major point that I want to make here is that there are different scales. There's the A scale, there's the D scale for harder compounds, and then there's an R scale. So when we talk about a 70 durometer O-ring, the A scale is normally used for rubber-type material. 70 durometer O-ring would be measured on the A scale, and normally would say 70 durometer shore A or 70 durometer A. Some urethanes and hydrauls might be measured on the D scale, and there is some overlap. You can see the relationship between the hardness of the D scale and the hardness of the A scale. A 45 on the D scale is going to be comparable to about a 92 on the A scale. So if you look at some U seals or some urethane seals, you may see some of them measured on the D scale, where it'll say 45 or 50. You may see some of them measured on the A scale, where it'll say 90 or 92 or 95. And some seals that are made up of two different urethane components may actually show two different ratings for the two different scales. So always remember that there's two different scales for measuring the hardness of the seals. So remember to think slim. Think seal shape. Think of the lip style. Think of an improver that you might use to improve the performance. And then finally think of the seal material. We've discussed a little bit of seal theory, principles of sealing, elements of seal design, and affecting the seal's performance. So we hope we've answered a lot of your questions that you may have had. If not, please feel free to contact us. We're more than happy to be of help. Thank you very much. We appreciate your listening to the seal seminar.